Okay, so question 64 is actually a pretty big question, but if you break it up into small parts, it's really easily handled as long as you deal with the small parts. Don't get freaked out with how much stuff you actually have to do. So sub-question A is asking you what product or products would get or be attained if you react a lot of different reagents, total of 8 different reagents with the same two alkenes. So first is cis-2-butene, and the other is trans-2-butene. The issue here is not so much what's going to happen, but the issue is being able to recognize what kind of stereoisomers you're going to get for this kind of question for each reagent. And you have to know like certain aspects of each particular reagent, whether it's stereospecific or not, whether what kind of mechanism you're gonna go through. But we'll go through a couple of different ones. So I'm only gonna go through 3 different reagents, and there are a total of 8. So these 3 should hopefully set you up pretty well to figure out how to approach the other sub-questions. So first things first, let's go ahead and try to draw out cis-2-butene and trans-2-butene. So we'll try to draw both these guys out, and it should get pretty easy after that point. So HCl. So the HCl we're going to have react with cis-2-butene. So the ene, we know we're going to have an alkene. The but is the butane, but it's butene. So methyl ethyl propyl butyl, so that's going to be 4 carbons in a row. And we know that the ene, or the double bond, is going to occur between carbons 2 and 3, or it's going to start on carbon 2. And then the cis is going to tell us that the 2 different sides are going to be on the same side. So this is the same way as saying Z or cis, same thing. So go ahead and draw them, these 4 carbons, and I'm going to go ahead and draw the cis configuration. So we're going to have carbon 1, 2, 3, and 4. And so this is carbon 1 and 2, so we're going to have our alkene here. And this methyl group and this methyl group are on the same side, or the cis side. So this is the cis-2-butene. So trans-2-butene is actually pretty easy from here. So we have trans, 1, 2, 3. So trans-2-butene. Okay, and so in both cases we have these reacting with HCl. So HCl. The easy way to think about this is having H+. Okay, and so this basically simplifies in a really easy way to just our electrophilic addition. So we're going to have our alkene acting as our nucleophile, H plus as our electrophile, or if it's easier for you to think about, you can say this pi bond is acting as a base, H plus is acting as an acid. So what we're going to do is we're going to have this double bond come over and attack the H plus, and now you have to kind of remember the mechanism that goes along here. So we have our carbocation-like mechanism, so we have to figure out whether we're going to put our C plus on carbon 2 or carbon 3. And in this first case, it's not too difficult because we have that mirror right here. So we know that we're going to have a secondary carbocation here versus secondary here. So it doesn't really matter. I'm just going to go ahead and put it on carbon 2. So we're going to have carbon 2 as our carbocation. So now what's really going to happen here, where the problem and difficulty is going to come from, is not the regiochemistry of what you're going to get. We already know at this point from our previous discussions that the next step is that chlorine is going to come in and it's going to end up attaching itself to carbon 2. So let's just go out and draw out the regiochemical products. Okay. So this is going to be our chlorine on carbon 2, and just for the sake of clarity, I'm going to draw out this hydrogen that's on carbon 2 as well. So this is carbon 2, carbon 3, carbon 4. So since we're in a chapter dealing with stereochemistry, obviously the question is asking you, can there be multiple stereoisomers? So going back to this sub-question A, if a product can exist as stereoisomers, show which stereoisomers are obtained. So the first thing you have to remember here is that because we're going through this carbocation-like mechanism, we can think of the carbocation as a planar molecule. So it's going to be sp2 hybridized, and sp2 molecules, or sp2 atoms, are going to be planar. Okay, so you can try to, if you were to draw out this carbocation, and I'm going to draw it out kind of like this, with, let's say, this CH3 coming out, and this is carbon 2, it's carbon 3 and 4, so I can just abbreviate this as an ethyl. So we have an ethyl here, and we also have hydrogen already still on carbon 2, so we can draw that hydrogen right there. And again, we have a positive charge. So thinking about this planar carbon in a three-dimensional way, that chlorine has a couple of different options here. It can either approach from the top or it can approach from the bottom. So that chlorine, that negatively charged chlorine, can attack from the top. So this is scenario A, or it can attack from the bottom, and that's scenario B. Okay, so let's go ahead and erase this guy right here. We already know the regiochemistry, which carbon that chlorine is going to go to. So let's just draw out both of the possibilities here. If we had chlorine attacking from above, let's say this is going to be completely vertical. So chlorine from above, and to keep everything constant, this ethyl group is in the plane of the board, so let's keep that in the plane of the board. We're not changing anything there. And also this hydrogen is pointing into the other room, so let's keep that the same here. So hydrogen is pointing back, and then the methyl group is pointing forward. So we have the methyl group pointing forward, so that's our methyl group. Okay, so that's possibility one, and then the possibility for other possibilities if you have the chlorine come from below. And in that case, we're going to have just the totally opposite result, in that the ethyl group is still, in the plane of the board, hydrogen still pointing back, and the methyl group is still pointing towards you. But in this case, the ethyl group is, the chlorine is coming from below. Okay, so chlorine's from below in the first scenario, and chlorine's from above in the second scenario. And you might have noticed that I kind of changed the orientation of whether or not the methyl group is pointing kind of down or kind of up. And that's just because you have to remember that after you add the chlorine, you have an sp3 hybridized carbon for both of these situations. So this carbon right here is sp3, and so is this carbon right here. So that means we have a tetrahedral compound, so we need to represent that in the way that we draw it. So we have to have that tetrahedral geometry. So those are the two different stereoisomers. So you can prove to yourself that these are different, one by trying to rotate them around, or you can do the formalism of trying to figure out R and S. So this chlorine is going to be 1, ethyl's 2, methyl's 3, and the hydrogen's 4. So in this case, this is S. Okay, and so in this case, very fortunately, still the hydrogen is pointing away from us. So this is still 4, this is still 1, this is 2, and this is 3. So this is going to be going clockwise, so 1, 2, 3. So this is going to be an R. So we have both an R and an S stereoisomer. And so because the connectivity is the same, because these are going to be mirror images of each other, we could draw them like that if we really wanted to. And they're not going to be superimposable. Because of all these things, we're going to have an enantiomer of this cis, so the cis-2-butene is going to give us enantiomers. I'm going to do the exact same thing with this trans-2-butene. So let's do the exact same thing. We know the same mechanism is going to occur. We're going to have this carbocation mechanism. We know we're going to get this intermediate with a C+, Cl-. The pi bond acted as the nucleophile, H+ was the electrophile, and then after we form our carbocation, this is now the nucleophile or electrophile, and the chlorine, negatively charged chlorine, is the nucleophile. So we can go ahead and show the attack. And we know that we're going to get the same kind of molecule, the same regio, or the same regiochemical product, in that we have that chlorine attached to carbon 2. Okay, so this is carbon 2 still, this is carbon 2 still. Again, the reason we get the same regiochemical product is that, again, just like with the cis-2-butene, you are really you're not really trying to figure out which carbocation is more stable, or it's not really making a difference, because this you're going to get a C plus on carbon 2 that's secondary if you attach to the um, carbocation here, or if you attach the carbocation to carbon 3, you're going to get a secondary carbocation as well. So in this case, it doesn't really matter. So we don't really have to worry about the regiochemistry. But just like for the first example, once you have this carbocation, you're going to have this planar situation. And once you have that planar situation, you can either have that nucleophile, that Cl minus, either attacking from the top or it can attack from the bottom. Okay, so you can draw this out again if you really want to, or you can just kind of think about it in terms of what you could potentially get for where the chlorine can attach. So we're going to have a chlorine either coming from the top, and we're going to have an ethyl right here and a hydrogen right here, or we can have it coming from the bottom, and it'll be the exact same result right here, chlorine from the bottom, and we're going to have the hydrogen still facing backward and the ethyl still facing forward. Okay, so in this case, 1, 2, 3, we're going to have an S, because this is going counterclockwise, and we're going to have, in this case, an R. 1, 2, 3. So an R here. So R and S. Notice we actually have the exact same molecule for reacting trans 2-butene as we do with cis 2-butene. So we have the exact same two possibilities. And it just so happened to be the way that the 2-butene is configured, that there is not going to be a difference in terms of the regiochemistry. You're going to get the exact same products. Okay, so that's the first bit. So in this case, to answer sub-question B, with which reagents do the two alkene that react give different products? For the HCl addition, we're not going to get different products. We're going to get the exact same product for both cases. Okay, so let's go ahead and prove that, just to make sure everybody's on the same page, because this got a little bit messy. So I'll try to organize it a little bit better. So hopefully we can all agree that these were the two products from the reaction of the trans 2-butene with HCl. So to prove it to you that we're getting the exact same molecule, so let's just redraw it. And I'm going to redraw everything with the ethyl group facing as far left as possible. So methyl, ethyl, and then we're going to have our chlorine, and we're going to have another carbon. Okay, so we're going to have a chlorine right here, and we're going to have a chlorine in an R and one in an S. Okay, so this is one situation, so this is carbon 2. And let's get rid of this guy. This was just, these numbers were just for figuring out R and S. Okay, so this is carbon 2, methyl, carbon 2 that has the chlorine, methyl, carbon 2 that has the chlorine, and then the ethyl right there. Okay, and then we're also going to have the other possibility. So this is the R possibility. And so we're going to do the exact same thing. We're just going to draw the S possibility. Okay, and again, I'm going to draw the ethyl group as far left as possible just to keep everything together. Okay, so ethyl and methyl, ethyl and methyl, and in this case this is going to be S. So all we have to do is switch the location of the chlorine and the hydrogen. So in this case, hydrogen forward, chlorine back. So this is still carbon 2, this is still S. Okay, so if we do the same thing for the top one right here, we're going to have an ethyl, methyl, and a chlorine. So ethyl on the left, methyl on the right, and this is going to be the S configuration. So 1, 2, 3, so that's our ethyl, then the carbon, then the methyl, and we're going to have this S configuration, like this. So chlorine in the back, hydrogen in the front. This is still carbon 2, and this is still S. Okay, so again, these are the two different results that we're going to get. Keep that in mind. This first result was from up top, so this guy is this guy. And same thing for the other stereoisomer. We're going to get an R instead. So all we have to really do is redraw this guy. So we're going to have an R, 1, 2, 3, 4, and chlorine facing front, hydrogen facing back, and this is carbon 2, and this is R. So notice that the order is slightly different, but you still get the same products. From the bottom scenario, you'd get an R and an S, R and S. And from the top scenario, you also get an R and an S. And the overall attachment points are exactly the same. So ethyl, methyl, hydrogen, chlorine, ethyl, methyl, hydrogen, chlorine, ethyl, methyl, hydrogen, chlorine, ethyl, methyl, hydrogen, chlorine. Okay, so we get the exact same product. So let's go ahead and start off with cis-2-butene. So in this case, for BH3-THF, you have to remember the regiochemical result as well as the stereochemical result. So we already know that if these are going to be hydrogens right here, we know that BH3 is going to end up adding in an anti-Markovnikov manner, and we also know that the final product is going to be an alcohol. So that means that we can have the alcohol attaching to an anti-Markovnikov position, but in this case, it's not really going to be different because we have the same number of hydrogens, so again, we can just kind of arbitrarily attach the OH to carbon 2. Okay, and that's what I'm going to do. I'm going to attach the OH to carbon 2, okay, and we're going to have the hydrogen that we're attaching from this BH3-THF to carbon 3. So these are going to be what's replacing your alkene. And so now we have to make sure we include all of our other initial attachment points. So we know we have methyls and hydrogens. So we need to go ahead and include stereochemistry. So back and forward, back and forward. And so we know that the methyls are going to be on the same side. So methyl group in back is one possibility, or hydrogen and hydrogen in front. Okay, so that's one possibility, and that would be if we had attack from the top. Okay, so then we also have the possibility of having attack from the bottom. So we can have our OH attack from the bottom, and we can have again wedge and dashes. So let's go ahead and attach our OH and hydrogen. So OH and hydrogen. So now we know that we can have still methyl in the back and hydrogen in the front. The important part here is that you're keeping everything on the same side. So since these two methyl groups are cis in the alkene, they must be cis in the product because unlike the carbocation-like mechanism, this is a simultaneous reaction where everything's happening at once. So you have no chance for rotation like you can with carbocations. Okay, so that was the top, and this is the bottom. Okay, so these are the two different stereochemical products that would result from BH3-THF followed by hydroxide, hydrogen peroxide, and water being added to cis-2-butene. And we have two possibilities. One where the BH3 attacks from the top, and then one where the BH3 attacks from the bottom. So obviously this is after the BH3 or the boron has been replaced by the hydroxy group. But we're not really concerned with the guts of how this is working. So we're just going to skip to the chase. So the problem here is that it's very easy to get caught up in trying to figure out stereochemistry, but there's a quick way to do this. So all we're going to have to do is figure out stereochemistry for 2 carbons, and then after that, the other 2 are going to fall into place. So let's go ahead and rotate this rightmost stereochemical product, where we're going to have the hydroxys on top, and let's go ahead and fill those in, HO and H. So all I'm doing is rotating along the x-axis by 180 degrees. Okay, 180 degrees rotation. And so now, since we're rotating along the x-axis, the methyl groups are now facing forward, hydrogens are now facing back. Okay, hydrogens back, methyl forward, hydrogens back, methyl forward. And so now we can easily figure out the R and S configuration of this carbon. So this is priority 1. The oxygen is going to have the highest atomic number, and then the tie is going to have to be broken between this carbon and the next carbon. So carbon-carbon, So we have a tie, so we have to move to the next available atom. And so the next one for the rightmost carbon is another carbon. The next available one for this carbon is a hydrogen. So carbon versus hydrogen, this one's going to win out. So this is 2, this is 3, this is 4. Okay, so 1, 2, 3, 4. 4 is in the back, so we have an R configuration here. Okay, and so now here, thinking about what we have for carbon 2, we need to ask ourselves, is this actually chiral? And the answer is no, it's not chiral at all, because we don't have 4 different groups attached. So we have a hydrogen and a hydrogen. So in reality, instead of 2, we only really have to figure out 1 stereochemical designation. Okay, so we have an R isomer here. And so if we look back to the left for the top attack, so if you look at the orientation, you have a methyl in the back, hydrogen in the front, and the hydroxy is facing up. So in this case, the hydroxy is facing up, hydrogen in the back, methyl in the front. So effectively what we've done between this stereoisomer on the left and this stereoisomer on the right is the single swap rule. So we already know the result of the single swap rule is switching R to S or S to R. Basically, we now know that since this is an R configuration, this leftmost chiral carbon for the top attack possibility has to be an S configuration, and you can prove that to you if you really want to. Just make sure that when you try to solve, you remember that the lowest priority is facing towards you, which is going to give you an incorrect answer. So it might look R, but in reality it's going to be S. Okay, so now we know that for this possibility we're going to have 2 different stereochemical products. So if a product can exist as stereoisomers, show which stereoisomers are obtained. So we did that. We did that for this first example. Okay, so now let's see if doing the same thing for the trans to butene is going to give us a different stereochemical result. So let's go ahead and draw out trans to butene. So there's our trans. And again, we have the possibility of attacking from the top or the bottom. Because there is no issue with figuring out Markovnikov versus anti-Markovnikov, and we're going to get the same configurational isomer whether you put the hydroxy on 2 or the hydroxy on 3. Again, I'm just going to attach it on 2, okay, just to keep things consistent. Alright, so in this case, we're going to get either the hydroxy on top, so hydroxy on top, OH, and H, and in that case we're going to have the methyl group facing either back or forward depending on how you want to orient yourself. So we have the back and the forward, and we're going to have a back and a forward. The issue here is that you make sure that since the methyl groups begin as trans, they also end as trans. Okay, so let's say we have a hydrogen coming down and hydrogen coming up. So let's say methyl's in the back, methyl in the back, hydrogen in the front. Again, totally arbitrary because we can rotate this guy, but just for the sake of consistency, I'm going to keep the methyl in the back. But we know that the methyls are trans, so if this methyl is in the back, this other methyl has to be pointing towards us to make them trans. Okay, so methyl in the front. Okay, so that's the top possibility, so the top attack point. So then we also have the bottom attack possibility. So if we have the bottom attack, just to keep it consistent, OH on the left, H on the right, and again we can have either the methyl in the front or the methyl in the back. Doesn't really matter because again we can rotate. What's important here is that we keep the methyls trans to each other because they're trans here. Okay, so methyl in the back, and hydrogen in the front, and in this case we can have the hydrogen in the back and methyl in the front. Okay, so again I'm going to do the exact same thing as I did before, and I'm going to do a rotation along the x-axis by 180 degrees just to make it easier to compare and contrast. So we're going to have this guy hydroxy pointing up instead of down, and because we're doing a 180 degree rotation, we're going to have this methyl group pointing forward and not backward. Okay, so methyl group pointing forward, hydrogen backward, and so again we're going to do the exact same thing with this hydrogen pointing up instead of down. And again, hydroxy was pointing down before, now it's pointing up. And so we just have to make sure we switch everything else as well. So hydrogen was pointing back, it's now pointing forward. Another group was pointing forward, now it's pointing back. So let's go ahead and figure out R and S. So again, for the same reason as before, where this was not a chiral carbon, this carbon is also not chiral because we have two hydrogens, so we really only have to worry about this carbon right here in terms of stereochemistry. Okay, so this is going to be carbon or priority 1 because of the atomic number of the oxygen, and this is going to be again priority 2, priority 3, priority 4. So this is also R. Okay. And so now we have an R possibility, and then what do we have on the left? So we have two different things to compare, one right here, one right here. So we have an R possibility on the left, on the right, and if you compare what we're changing, all we're really changing is H and Me. So because we're only changing H and Me on the left versus the right, we're going to have the single swap rule kind of configuration or scenario, where this leftmost carbon is S. Okay, so leftmost carbon is S, rightmost carbon is R, and again, all we're really getting in this case are enantiomers. So we have enantiomers here, and we also have enantiomers on the top. Okay, and overall, we're going to end up getting the exact same product. So you see how we have an S on the bottom, S on top, and achiral carbon here, achiral carbon here, R and R. So to answer the second part of the question, with which reagents do the two alkenes react to give different products? In this case, we will not get different products between the two different starting materials. So the starting materials actually give the exact same products, SR, SR, but each starting material will give two different stereoisomers. So both will give an S and both will give an R. Now, if you really want to blow your mind, you need to think about the possibility of what would happen if instead of this being a methyl, what if it was an ethyl? What if there was an ethyl here, or what if this was an ethyl here? So this is another really good time to play around with this. So instead of a hydrogen being there, what if this was an ethyl? And then instead of a hydrogen being here, what if this was an ethyl? So these would make really interesting starting materials to play around with to see if you would still get enantiomers, or would you potentially get diastereomers, or would you potentially get different products between two different compounds. So you might want to play around with these. This would be cool. Okay, so the last sub-question that I'm going to go through is Br2 and water. So again, we're going to have the same starting materials. We're going to have cis, and we're going to have trans. Okay, so same thing as before. We have to remember the regiochemical results of Br2 in water, and we also have to remember the mechanistic effects of how Br2 in water adds. So Br2 and water is going to end up adding in an anti-fashion. So you have to remember that this is a halohydrin formation. So unlike Br2 in dichloromethane, if you have a lot of water in solution and you adjust the conditions just right, you can have not two bromines adding, but you can have a Br adding for the bromonium, and you can have water acting as a nucleophile instead. So the two things to remember is that one, this is going to be an anti-formation, and then you have to play around with where things are going to go. Okay. So again, we have hydrogens, and we can again either have bromine attack from the top or the bottom. So in this case, we have a top attack, so we can have bromine on the top, and OH is going to be on the bottom as a result, because this is an anti-addition versus the boration. So the hydroboration oxidation was a syn addition. So in this case, the Br and the OH are going to be on opposite sides. And because, again, there's no chance for a Markovnikov or an anti-Markovnikov, this is actually relatively simple. So we have two different other location or attachment points, and one's going to go back, and one's going to go forward. So again, the methyl groups are in the same position, so we're going to have a methyl just arbitrarily coming forward, hydrogen going backward, and so since one hydrogen is going backward, the other one must as well. Okay, hydrogen and methyl. Okay, so in this case, that's the anti-top attack, and we can also have an anti-bottom attack. So we can have bromine from below and hydroxy from above. So we can have a methyl group coming out, just like before, and hydrogen going in. And same thing as before, you can have a hydrogen going out or back, and the methyl coming forward. So again, the whole idea here is that the two methyls are exactly the same. They're syn to each other. So these two methyl groups are syn to each other, and immediately after the reaction, these two methyl groups are syn to each other as well. So these are syn, or this is still an anti-addition, but this is from bromine coming from below. Okay. So again, the bromine comes from below to form the bromonium ion, and then the water acts as a surrogate towards the other bromine that would have attacked from the bottom as well. So these are the two different possibilities for the cis. So we can go ahead and figure out stereochemical designations for this guy. So bromine is going to be 1, and then hydrogen's 4, and then this carbon over here is going to be 2, this is 3, so 1, 2, 3, this is going to be R. Okay, so R. And then the question you now have to ask is, well, will we actually have a chiral center on the right this time? And indeed we will. We're going to have a chiral carbon on the right as well, so this is going to be even more complicated. So we have a hydroxy, which is 1, and this hydrogen is 4, and then for the same reason as before, this leftmost carbon is going to be 2, methyl is going to be 3. So this is going to be an R as well, so we're going to have an R and an R. Okay? So this is going to be RR, and now we're going to have potentially a different product. So let's go ahead and do that same thing and do that 180-degree rotation along the x-axis just to keep things as similar as possible. So I'm just going to rotate this guy in my head, have the bromine pointing up, and hydroxy pointing down. And so now we have hydrogen now facing forward, methyl now facing backward, and now we also have the methyl facing backward and the hydrogen facing forward. Okay, so this is going to be very similar to the one on the right. So let's go ahead and highlight what we're comparing. We're comparing this guy to this guy. All right, so thinking about this configuration, bromine's facing up, bromine's up, and this whole bit's the same, it's just on the right. Okay, so the 1, 2, 3, 4 priority isn't going to change. The only thing that's changing is the orientation of the methyl and the hydrogen. See how this methyl's facing out, hydrogen facing in? Hydrogen's facing out, methyl's facing in. So since this carbon is R, this carbon must be the mirror image, which means it must be S. Okay? And so for the same reason, since this is R, this must be S. Okay? So for the products that we're going to get here, we're only going to get 2 different stereoisomers. So we're going to get an RR and an SS. And overall, in a very interesting turn of events, these are actually enantiomers to each other, just like the other ones were. It's just a difference, slightly more complicated enantiomer. Okay? So now let's do the opposite and see what we get for the bottom. So this was the cis 2-butene. This is the trans 2-butene. So trans is going to look like this. We're going to have the same 2 scenarios. We're going to have bromine on the top, bromine on the bottom attack. So bromine and hydroxy. So again, because we're using water and not some kind of aprotic solvent, we're going to assume a halohydrin formation. So in this case, we're going to have one group going back, one group going forward. So since I've had this designation of up being, in the front, I'm just going to go ahead and keep with that. So a methyl group in the front, hydrogen in the back. And so since this is a trans configuration, so methyls are trans to each other, that must mean that this methyl is in the back, this hydrogen is in the front. Okay, so now all we have to do is do the opposite. So this was the anti top configuration, this is going to be the anti-bottom configuration. So again, bromine's on the bottom, hydroxy's on the top, and we're just going to do the exact same thing. Keep the methyl in the back, keep the hydrogen in the front, and we're going to have hydrogen in the back this time. Same thing as before, and methyl in the front. Okay. Alright, and again, just to make it easy, you can do that 180-degree rotation. You don't really have to if you don't really want to, but sometimes it makes it easier. Another way you can do it, now that I think about it, let's try it this way, just to make things a little bit simpler. I'm just going to move this guy down a little bit. So if you think about the way this is oriented, we basically have a mirror image. So if you drew a mirror image going across like this, you have the hydroxy pointing up, bromine pointing back, methyl pointing into the other room, and hydrogen pointing towards you. So this is a mirror image, and this is another mirror image. So hydroxy is pointing towards each other, methyls are staying back, hydrogens are facing, the hydrogens are facing back, and the methyls are facing forward. So in this case, we know that whatever stereochemical configuration we come up with for the one on the top, we're going to come up with on the bottom. Okay, so in this case, we have hydrogen in the back. This is the easiest one to do. So let's go ahead and do this guy. So this is 4, 1, 2, 3. So this is R. Okay, so this is R. And so now you can either rotate this if you want, or you can imagine yourself looking from behind the molecule and positioning yourself behind. That might not be the easiest way to go about it, so maybe we can do a little rotation along this bond. That might be an easier way for you to see it. So if we do a rotation, I'm going to keep this rightmost bit constant, and I'm just going to rotate a little bit. So keep this bit constant, hydrogen, methyl, and OH. And so we're just rotating along the carbon-carbon bond. And so we'll have this bromine facing down, and hydrogen facing back, and the methyl facing forward. Okay. So all we've basically done is we've done that same kind of 180-degree rotation, but we've done it along this carbon-carbon bond. So since the bromine was originally up, it's now down. Since methyl was originally back, it's now forward. Since hydrogen was originally forward, it's now back. Okay, and we already know that this is R, and we're not doing the single swap rule here, so we don't have to worry about messing anything up. So we still know 4, 1, 2, and 3. So 1, 2, 3, this is S. Okay, so we have an SR configuration. Maybe if I draw it out with a different color, it might make things simpler. So this is S, and this is R. Okay, so if we were to number these carbons, so this is, let's say, carbon 1, 2, 3, 4. This is still carbon 1, 2, 3, 4. Okay, so we know carbon 2 is S, carbon 3 is R for the first possibility. So that must mean that carbon 2, 1, 2, for the second possibility must be the enantiomer. So this is R, and this must be S. Okay, so we're still getting enantiomers for the trans 2-butene, but this is the first example where, you know, that second bit, with which reagents do the two alkenes react to give different products. This is the first scenario where we have two different products being formed. We have an RRSS enantiomer set being made for the first molecule, okay, and for the second molecule we have an RS-SR molecule set being made for the second molecule. So we're getting two different diastereomers that are being formed. Okay, so these two right here, these are enantiomers, and so are these. These are enantiomers as well. But if you compare either one of these, either this one and this one, or this one and this one, these are both diastereomers. Okay, so that's the first situation we've seen where you can get different products using the same reagents from two different starting materials. Okay, so that was a lot, and it takes a lot to get used to this kind of stuff, and it can be tedious, but really, as long as you practice, and I would definitely recommend practicing the rest of these, um, ideally, if you don't have to talk it out, it won't take 43 minutes like this has taken me to go through, all three of these examples, but you can go through them very, very quickly if you don't have to talk. Um, so again, definitely practice the rest of these, and hopefully these start to make sense or start to get a little bit easier. But at the very beginning, they're definitely difficult. Try not to get frustrated. Just take them problem by problem, and eventually they'll definitely get easier, I promise. Okay? All right, good luck.